चले अब सब please everyone need to pay attention here. Magnetic field strength. So check your notes. Last time I think we started this article, right? Check the notes. We started this chapter, magnetic field strength, and I think we have started this definition also. If anyone has a record, so you can share. The title we were discussing, the chapter name is magnetic field. This is the largest chapter we have, the most important in its size. We introduced the concept of magnetic field. So anyone can recall what's the definition for magnetic field? Magnetic field is an example of field of magnetic field is an example of a field of force produced either by moving charges or by permanent magnet. Remember, I told you people that what chapters are related here from IGCSE from O level, what chapters are connecting here. The first chapter was magnetism. The second chapter was electromagnetism. And what was the third chapter connecting here? Electromagnetic induction. This chapter is a combination of those three chapters. When a charged particle moves, it produces a magnetic field. And this chapter was in our O level. What was the other concept to reconnect? Ahmed, look here. What was the other concept? The other concept was that when you have to show a force field is an imagination. So when you have to show a force field, you always have to use virtual lines, and these virtual lines are called flux. Flux is an imagination. Here, the field lines are always directed from north to south, outside the field, outside the magnet. And what was the unit of magnetic flux? Weber. And the unit of flux was Weber. It was a scalar. This is the left one. It is a horseshoe magnet, and this one is a bar magnet. Now this is a bar magnet. Outside the magnet, the field lines travel north to south, and inside the magnet they travel south to north. How we show the direction of magnetic field? When you are showing curves, you will draw what? You will draw a tangent at a point to show the strength of the or direction of the magnetic field. Now, I think we were somewhere here, or we have crossed it. Islam. Check the notes. So, yes, magnetic field strength. What was the definition? Magnetic field strength is defined as the magnetic flux linking per unit area. So now this is a mobile surface. Lot of magnetic field lines or Wi-Fi signals are supposed here. Some of them are cutting through the surface. That particular part which is passing through an object is called flux linkage. Now look at the formula for magnetic field strength. Magnetic field strength is defined as what? Flux per unit area. What's the definition? Or sorry, what's the unit? Weber per meter square. Then what was the definition of flux? What was the definition of the flux? Flux is the product of magnetic field strength and cross-sectional area. Now, is this formula there in this way? This formula, this box is there or not? It's there. Okay. Then the concept of flux linkage, we had played this animation in my record. Now, if I consider this hole is called flux. And if I consider only these lines, then what is this called as? Flux linkage. And what was the concept of the formula? Look, the formula here. The formula for flux linkage in our first approach, what was the formula? P a sine theta. And then why we introduce the concept of N? What is N? Number of turns. So the formula will become, the formula is now how much? What's the formula? The formula is NBA sine theta. And this formula shows maximum or minimum values. If the if the object is perpendicular, the flux linkage will be maximum. If the sheet or the object is parallel to the field, then the flux linkage is minimum. Now, we had to remember that n, in a single calculation, if n appears twice, you have to remember that for the second entry, you have to put the value of n as 1. I think we should start from here. Let's start from this point. Okay. Now, start from here. Okay. This one. In a single calculation, if n appears twice, this will be more explained when we do a question. In any question, if you are calculating magnetic flux, suppose you calculate n and you get the value of n. So if n comes again in the same calculation for the second time, you're not supposed to put the real value of n. Suppose in a question, n is equal to 200. You first calculate the flux NBA sine theta. Now, suppose after that, n comes again in another formula, phi upon t. For the first one, you put n is equal to 200. But for the second entry, you won't put n is equal to 200. You put n is equal to 1. So now this is the point which we should make it as our first concept because we revise everything. So now you have to copy this screen as the first title, put the date of today. Chapter name is magnetic field. We have finished capacitor. We have finished capacitor. We have completed electric field ASA2. We have completed gravitational field. We have completed circular motion. So this chapter is magnetic field. Put the date of today. This is going to be the first concept. This is the calculation concept. If n appears twice, if n appears twice in any calculation, if n appears twice in any calculation, you have to put n is equal to 1 for the second time. Now let's summarize what we have discussed. There are two formulas for n. Phi is equal to NBA sine theta. Phi is equal to NBA cos theta. Now, please carefully see this feature because whenever there are two matching formulas, you should know what's a default formula. The default formula for flux linkage is NBA sine theta. The people who are taking math should know that cos 90 minus theta is equal to sine theta. This is only a mathematical difference. So let's put it as our second title. There are two formulas to calculate magnetic flux linkage. What are the two formulas? Phi is equal to NBA. Achha, what is phi? What this symbol means? This one. What this symbol means? Magnetic flux linkage. Magnetic flux linkage. What the letter N stands for? Number of turns. What the letter A stands for? cross-sectional area. So now you have to copy this screen. This is our second concept for today. There are two formulas for magnetic flux linkage. One contains sine theta and other contains cos theta. Now, please look at this idea that how we apply these two formulas. Please look at the screen. We have two formulas to discuss. One is having a cos function, one is having a sine function. Now, look at this idea here, the angle. Look at the angle position. Now, this is a surface. Look, this is a surface. ऐसे हम बना ले. And these are the magnetic field lines going on. Now, this is the direction of the magnetic field, and this is the surface. Now, this angle theta, if you make the angle theta from this side, you will always use the formula phi is equal to NBA sine theta. If this is the surface, you put it like this, magnetic field is coming in this orientation, theta will be 90, whatever angle you can take. In the second option, look at the second option. I draw an arrow on the surface of the sheet. And these are the magnetic field lines going on. These are the magnetic field. Now, this is the area of the surface. This is magnetic field. If I take this angle theta, then I will apply the formula phi is equal to NBA cos theta. This is the difference. If you draw an arrow on the surface and you take angle with that surface, you will use cos. Otherwise, if you take the angle with the surface of the sheet, then you will apply which angle? Formula? Sine theta. For example, this door, is it perpendicular to the floor? This door is perpendicular to the floor. I'm taking angle between the vertical surface and the floor. Then what formula I will use? Achha, now, if I draw a perpendicular on the door like this, now this perpendicular and this floor, are they perpendicular or mutually parallel to each other? Good. In that case, you will use which formula? Cos theta. So this is a mathematical translation. Otherwise, the main concept will remain the same. Now we move to our next concept for today. Give the heading magnetic field of the earth. We are putting the next concept, magnetic field of the earth. This is our next concept. Now we have to put a simple concept that our planet produces a known magnetic field, which is known, but not very strong, not strong enough to disturb our activities much. If you put a magnetic compass anywhere, the compass will deflect in the direction of the earth magnetic field. Look at the strength. Look at the strength of the earth magnetic field is only how much? 25 to 65 micro Tesla. It's a very weak field. It's a very weak field. So remember this concept that Earth produces a weak magnetic field which is produced around the planet. So the heading is magnetic field of the Earth. It is present, but it doesn't interfere with the functions on the Earth, like electric wires are going on above the Earth. We use metals in our buildings, especially iron is used, but Earth does not disturb them. I repeat the two concepts. Number one, Earth produces a weak magnetic field. How much weak? It is approximately 25 to 65 micro Tesla. Number is not required. The concept is required that Earth produces what type of magnetic field? Very weak field. Second concept, this field, this field is noticeable on a magnetic compass, but it doesn't interfere with our electrical systems, with our satellites, with our normal functions involving iron. So these are the two concepts. So give the heading magnetic field of the Earth, and you have to write down the first concept. Earth possesses, right after giving the heading, this is the heading, okay? After giving the heading, right under it, Earth produces a weak magnetic field. Earth produces a weak magnetic field. Next line. A magnetic compass can detect this field. A magnetic compass will detect this field. Next line. In common practice, this field does not interfere. In common practice, this field does not interfere, with common activities like electric wires carrying current, does not interfere with common activities like electrical wires carrying current. Now these are the two concepts. Now we introduce the title electromagnetism. This is our next title of the chapter. Remember, the name of the chapter is magnetic field. It's a mega chapter. It's a heavyweight chapter. I repeat again, there were three chapters in our IG, in our O level, which are merging here. What are the three chapters? Magnetism, okay, everyone please give the heading. Everyone please give the heading electromagnetism. Give the heading electromagnetism. Let's see our O level memory to be back or not. Whenever current passes through a wire, it produces a magnetic field. This phenomena is called electromagnetism. So look, one magnetism is in our life from a very earlier time. We have little magnets in our homes. Some people have a memory of sticking the magnets on the doors of AC and playing with magnets. Those are called permanent magnets. Magnets are in our common life a lot of ways. Door catchers, videotapes, computer drives, everywhere. Now, here we are talking about a magnetism which is not due to a power magnet. This magnetism, which we are now starting, is due to what? electric current. So repeat, what topic we are starting within the same chapter? Chapter is same, but we are starting a new title within the chapter. What's the name of the title? Repeat. Please try to repeat, because you people have done this topic. If you repeat 1 or 2 or 3 times, it will come back. Human memory is organic, so it keeps on flashing. So now, after giving the heading, right under it, magnetism due to current is called electromagnetism. Right under it, everyone. Magnetism due to current is called electromagnetism. Magnetism repeat, magnetism due to current is called electromagnetism. Now remember that the first example of magnetism for our common experience were those bar magnets. Remember, we had those bar magnets like this, one side painted red, one side painted black. They were in our common labs. Magnetic compass is another example. Now we recall our O-level very important concept that magnetism can also be produced by electric current. So when these wires, look at this wire has current. So physics says along with current, it is also producing magnetic field. This magnetism, which is produced by electricity, is called. Okay. Now we move to our next title within the same chapter. Give the heading Origin of Magnetism. Give the heading Origin of Magnetism. We started this chapter a week back. Then we had to stop. We were doing past papers and we were covering those work. And now we are back on this chapter. That's why I did a revision in the start of this chapter. Origin of magnetism. Now that's very important to understand that when a charged particle moves, when a charged particle moves, it produces a magnetic field. Look at this wire. Does it contain moving charges? What moving charges? Electrons. Very good. So when charged particle moves, easy words, when current is there, whenever a charged particle moves, it produces, whenever a charged particle moves, it produces magnetic field. So after giving the heading origin of magnetism, you have to write down in inverted commas, which is a core concept of this chapter, right under it, whenever a charged particle moves, whenever a charged particle moves, it produces a magnetic field. Whenever a charged particle moves, it produces a magnetic field around it. Whenever a charged particle moves, it produces a magnetic field around it. Now, this is a charged particle moving. This is an electrical wire. A charged particle is moving and it produces a magnetic field. Now, remember, what is the letter P in this chapter will be going to represent? Magnetic field is, do you remember in gravitation, you people must have noticed a pattern that now they do not use the word strength. They use the word magnetic field. It includes the concept of magnetic field strength. It's a signal strength. So repeat the concept. The title we are starting is Origin of Magnetism. What is the origin of any magnetism? What is the origin? A charged particle which is moving. For example, in an atom, electrons are moving around the nucleus. This is a moving charge. When charged particle moves in a straight line, we call it as what? When charged particle moves in a straight line, this is called current. Now look at these circles. These separate circles, they represent magnetic field. So I put my next concept for today. When a charged particle moves in a straight line, it produces shape, circular magnetic. I repeat the concept. When charge particle moves in a straight line, it produces magnetic field, and the geometry of the magnetic field is circular. Once more, repeat. Concept is important. You can write it always. What's the concept? When charge particle moves in a straight line, it produces circular magnetic field. So now there are three concepts to connect. Number one, first concept, we are starting a topic, electromagnetism. What is electromagnetism? Magnetism due to current. Second concept, what is the origin of magnetism? The origin of magnetism is the motion of a charge particle. Third concept, if charge particle goes in a straight line, now this is a wire, charge particle is going like this, it will produce circular magnetic field. Now these three concepts have to be connected. Now you have to copy this. Copy this. So we have reached here. A charge particle moving in a circle produces a magnetic field. Now we come to a very important concept of our previous chapter. Before capacitor, we did a chapter which was named under, what was the name of that chapter? What is electric field? Electric field is a region around a stationary charge in which another test charge experiences a force. Now, let's make our next very important concept. If a charge particle is at rest, it will produce electric field. And when a charge particle is in motion, magnetic field. Repeat the concept. Very important concept of this chapter and the previous chapter. What's the concept? If a charge particle is not moving, it is at rest, it will produce electric field. And as soon as begins to move, then good. So now you have to copy this very important connecting concept. Copy this concept. So this is our concept, charge particle in motion and charge particle not in motion. Now we move to experiment to show electromagnetism. Give the heading, experiments to show electromagnetism. Remember, when this word experiment come, you should understand that in paper 4, they do not go for experiment. They do not ask you to draw apparatus working. Paper 4, paper 4, paper 4 is a solid theory paper. Today is the retake paper 4. So paper 4 is a 2 hours fully loaded theory paper. Your formula memory, your derivation memory, your description memory, they will test everything in the memory aspect. So huge number of formulas are there, derivations are there, descriptions are there. But when it comes to experiment, then it is actually connecting to paper 5. In paper 5, right now, we are doing side by side what questions? Design questions. So automatically you should remember, because obviously paper 5 itself have no separate theory. So you should automatically remember that when I discuss an experiment, by default, experiment goes for paper 5. Now remember this idea. Remember this idea that whenever electric current passes through a conductor, it produces a magnetic field. Acha, after giving the heading, right under it, after giving the heading, right under it for paper 5. Right under it for paper 5. Now, this is a very good website, and anyone who is interested in simulations, you people know, because here we have some smart people who are making robot also. So you people know that what is simulation. Simulations actually mean that you can run something in virtual environment. Nowadays people talk about AI and other things, but AI is something very much advanced than this, but this is very nice to use. I will post this link also, and I hope it loads here, but it's taking time. Now, simulations are actually showing these type of phenomena. Now, this is a simulation, okay? Simulations are very impressive. Like, for example, you are practicing something, so labs are not there. In in A2, there's no lab, but see, I expect that you people go to a lab. Can you people see a magnetic compass here? And a long solenoid. Anyone remember the word solenoid? This one, coiled one, is the solenoid. Now, can you see the magnetic compass? Okay. Now, this is the magnetic compass. Now, it's a simulation, so I can move. I connect it here and I connect it here. Is it necessary to see the plus minus when you connect something? Otherwise, the famous our Pakistani logic, reverse it. If it works, okay. Otherwise, reverse it again. Now, can you see the compass again? What compass is presently showing? Is it showing Earth magnetic field? It is presently showing the magnetic field of the Earth. Achha. Now I'm planning to switch on the current in the system. Now I release some current. Look the direction of the compass. Can you see the change in direction? If compass needle, if compass needle deflects, what it shows? Current has produced some magnetic field. Okay, now I can do one thing. I can take out the connection. What the compass has done? Compass is back. It means no more magnetic field. Achha, if I remember this concept and I put it again, now again compass shows what? What it means? When current passes through a conductor like a solenoid, it produces magnetic field. Now, this is a compass, this is a solenoid, and we have a switch. Now, you have to copy this. Now, right under it, when the switch is closed, when the switch is closed, when the switch is closed, the compass needle shows deflection. When the switch is closed, the compass needle shows deflection. The compass needle shows deflection. Now we put our last concept for today, that why we use electromagnets. Now electric trains, electric vehicles, electric devices, our gadgets, trains, vehicles, electromagnets are always there. Now even in Pakistan is claiming to going to have the first bullet train. But we are claiming that we are going to launch the first bullet train, inshallah. Now, what is a bullet train? It uses an electromagnetism, and the train is elevated, not touching the ground. So, what are the important two benefits of using electromagnets? The first one, you can control the magnetism. Whenever you want, you can switch it off. Whenever you want, you can switch it on. Secondly, you can control the strength of the electromagnet. You can pick a whole container, you can pick a whole ship, you can pick a big size any object, but you can also control to pick a small piece of nail. So now right under it, that electromagnetism has some important benefits. Right under it, electromagnetism has some important benefits. Some important benefits. Roman numbering. Number one, it can be switched on or off when needed. It can be switched on or off when needed. Number two, its polarity and strength can be controlled. Its polarity, and strength can be controlled. Now, we have to put a heading, give a gap of at least, we always give a gap of 2 lines when we get a new heading. Same chapter, magnetic field due to a straight current carrying conductor. Give the heading for the next class reference. Heading is there, magnetic field due to a straight current carrying conductor. Okay, so we are stopping here. This is our title for the next class. The chapter name is magnetic field.